Hello, Internet, and welcome to Framework HQ. I am here today with Nirav, and we are going to talk about RISC-V, deep computing, and all the cool stuff that's happening in that department. So Nirav, I heard that someone slid into our DMs and this is how this all started.
Yes, this all started with a tweet. We get a lot of tweets, we get a lot of DMs, and not all of them go somewhere, but sometimes there's a gem in there. So actually last fall, Yuning, who's the CEO of DeepComputing, actually tweeted publicly about something related to building RISC-V mainboards for laptops. And I actually reached out to him and said, like, hey, I saw your tweet. That sounds really interesting. We should actually chat about it, and provide my email address. And then he reached out. And I assumed this would go like 90% of those tweet exchanges and DMs go, which was just, a fun conversation, brainstorming about some cool stuff, and then just departing. But actually, Yuning kept coming back over and over again with like, hey, we did this thing. And every time he'd come back with an email, I would just be shocked because like I would have assumed like, oh yeah, like, his first pitch was basically, hey, we're just going to build a mainboard for your laptop. And I'm like, okay, here's the documentation. Go have fun with it. Expecting that nothing would come out of that. But he came back a few weeks later, basically with like, okay, here's the architecture. It's done. And then I thought like, oh, okay, we better start taking this seriously. And then each time beyond that, he would just keep coming back with more and more progress until we got to actually a functioning RISC-V based mainboard, which is our first ever third-party developed mainboard for Framework laptop.
Wow. So how long did it take from that first DM to this?
Yeah, that was in November. We're in July now. But actually, the team there really seriously got started just a few months ago. So they've been making just massive, rapid progress on this.
Oh, wow. That's actually pretty crazy. That's an insane turnaround time for hardware.
Yeah, absolutely.
Wow. So for those who are new to the world of open source hardware, what is deep computing and what is RISC-V?
Yeah, this is an interesting one. So DeepComputing is a startup based in Hong Kong that really has focused their entire company around this idea of enabling the RISC-V ecosystem, basically by building devices. And so obviously we have to rewind a bit and explain what RISC-V even is. And so RISC-V is an open instruction set architecture. And so if you're not familiar with instruction set architecture and ISA, basically it is the interface, the definition between the actual hardware, the actual physical compute hardware of a CPU and the software that runs on it. It's like a standardized set of instructions that software is compiled down into and turned into machine code that then actually gets parsed by the CPU itself to execute an operating system and a program and so on. And obviously there have been a large number of ISAs over the course of decades. The entire industry of computing is based on this idea that you can define a common instruction set between hardware and software, so you can build a software ecosystem around hardware. But they've all been proprietary. For the most part, they've been proprietary. And if we look at like the broad compute market today, it's really x86 and ARM. And so x86 is an instruction set architecture that was invented by Intel back in the late 70s. It is obviously proprietary to Intel, but there have been third parties like AMD who have built x86-based processors, and Intel and AMD have this cross-licensing agreement. But basically, if you are a company wanting to build an x86 computer, you can only get that processor from either Intel or AMD, effectively. So it's not so much a rich, wide ecosystem in the way that maybe if we think about like Linux, for example, as a software ecosystem would be. ARM is a bit different. So ARM is actually one company that has defined a instruction set architecture called ARM that is licensable. So if you're a company that wants to make a chip, you can license this ISA from ARM, make your chip, sell it out in the open market. And ARM has basically a pretty broad range of ISA, or a bunch of cores basically, and a pretty extensible ISA that goes from like the tiniest little microcontrollers all the way to pretty giant processor cores that can go into things like laptops or servers and so on. And so basically all this is just context to explain that as we look at the world of compute today, there are really only two options. They're both proprietary. There's either x86, which is proprietary Intel and AMD, or there's ARM, which is proprietary ARM, and like somewhat licensable, but there's never been like a broad open ecosystem that could enable the richness of basically ecosystem power that we see out of something like Linux, like this world of open cores, open processors, open hardware, open software that's all interoperable. And so RISC-V was really the first attempt at doing that.
So if I'm understanding this correctly, if I wanted to create my very own mainboard and I wanted it to run x86 or ARM, I would have to pay a licensing fee for x86 or ARM to run on this mainboard.
Yeah, this is a tricky one. The interesting thing there is that you actually basically can't, no matter how much money you had, you actually can't license x86 effectively. There have been some like very, very rare exceptions over the course of decades, like Transmeta and VIA had done some things in the distant past. But basically, if you want x86, you are buying a processor that either Intel or AMD has designed and manufactured. So there's a very limited number of processors. There's a very limited range of flexibility of processors that are available. Now, if you wanted to design your own processor, you could go and license a core from ARM and basically design your processor around ARM cores. But even there, you're limited in flexibility. You basically have to play within the box that AMD or that ARM rather has defined for you.
So with RISC-V, you can basically do whatever you want because you get the full IKEA instruction booklet on how to build your thing.
Right, yeah, and this is an interesting one because there is this ongoing kind of balance between fragmentation on one hand and flexibility on the other hand. And this idea behind RISC-V is that by having a centralized organization called RISC-V International that actually manages this instruction set architecture, they can kind of pick a good balance there. So what RISC-V has done, the actual organization has done, is basically manages and fosters the definition of the ISA. So there's like a core ISA for RISC-V, and then there's a number of extensions that people can add to it. But each of those things are actually governed and ratified through this, I'm pretty sure it's a nonprofit organization. And so the idea there is that, like, if you even wanted to extend on the ISA, you could actually propose an extension, design and develop it, bring it into committees, and then standardize and extend on it. And so it basically like gives you this balance where like you can continue to build on top of RISC-V, but it's not like a total Wild West free-for-all where like stuff's just incompatible because people are inventing whatever they want and like hacking it together. So it's this like really, really interesting balance.
It's almost like a scientific method approach to like a very scientific IEEE style approach to doing like open source and community based hardware design, where it's not just consolidated to one company. Everyone can contribute and everyone can help like move it forward.
Right, definitely. And the cool thing about it is RISC-V actually did come out of academia. So there's there's a group of people in Berkeley a group of professors basically who were actually trying to come up with an ISA or like a core to use for research and academic purposes because like it didn't really make sense to like attempt to license like something proprietary like ARM and then build on it for research. It just wouldn't be a fit. And basically in the process of developing this about 2010, 2011, they kind of came to the realization that like this is not just useful for research. This is actually a really interesting way to unlock basically the entire future of computing to be more open and unconstrained than something that's controlled by basically 2 or 3 big companies.
I love that. Go Bears.
Yeah.
What makes this deep computing mainboard different from all of the mainboards that we released?
Yeah, so I guess we can just dig in, kind of starting from that description of the RISC-V ISA, the architecture, out to like the actual physical hardware we have in hand here. So like going back to this cool thing about RISC-V being open, so there's a company called Sci-Fi that was one of the earliest companies in the RISC-V ecosystem that actually took that ISA and developed core IP around it. So basically the ISA is just that like almost recipe for that interface between the software and the hardware, but actually doesn't define the entirety of the processor. It doesn't even define the entirety of the CPU. It's really just almost that like hardware interface language from the hardware to the software. And so you need basically the next layer of companies in the stack. So think about like the bottom layer being this like almost DNA of the computer being the instruction set architecture. Beyond that, you need like I don't know, or if we're doing, I'm not a biologist, this is not going to go well, but I don't know, like proteins or something like that.
Yeah, we go from amino acids to
Yeah,
proteins.
we're going to amino acids, now it's just like proteins and cells and things. But anyway, so that this company, Sci-5, developed a series of cores. And so they've continued to advance their cores over the course of the last decade or so now. And they built a core called the U74, which was one of the first actually kind of like commercially competitive cores for like compute applications. So early on, of course, a lot of the RISC-V cores and like designs are focused more around like microcontroller embedded type stuff, really, because it's just very straightforward to start from that. But Sci-5 went and developed these pretty competitive compute cores. And they're not the only ones. Now there are a number of core developers out there, including ones that are actually open sourcing their actual CPU core designs. So basically, Sci-5 built that core that was pretty competitive, and that actually in part enabled an ecosystem of chip developers to then take that core and turn it into an actual processor, like an entire chip. And so we're keeping biologists and maybe getting to like organs or something.
Yeah.
It's like we built a kidney here with a chip. So the existence of the Sci-5 core enabled companies like Star5, which is actually the company that built the chip here, that's called the JH7110, to create this processor. So basically they licensed this core from Sci-5 that uses this underlying open source RISC-V architecture. They added a bunch of peripheral IP, things like interfaces for USB and PCIe and display outputs, a little GPU, and then turned it into that JH7110 chip. And of course, a chip is just a chip. You can't use a chip on its own. And so like if we're thinking about the next set of that ecosystem, we've got like the entire human being or something is this board that Deep Computing built. So Deep Computing took that Star5 chip, designed a mainboard around it, and of course designed it in a way that it fits into a framework laptop. And all this goes back to this idea of like, why did we reply to that tweet to begin with? Why did we think this was interesting? It's actually that the entire philosophy behind Framework is the idea that an ecosystem is more powerful than the sum of its parts. And RISC-V fits that philosophy perfectly. So this idea that you could have this open ecosystem that's built around an ISA, and this idea that you can have this open ecosystem built around basically keeping hardware stable and long lasting was just this perfect fit.
So one of the things that makes this board a little bit different is that there are some soldered components on there.
There are. So this is an interesting one. I guess we can dig into like what this actual board is. And one thing that we want to be like really clear on is that this today, it's not intended to be a consumer-ready mainboard. It's really intended to help foster and enable this RISC-V ecosystem by getting basically a consumer-ready form factor, but with a board that's more intended for software developers and tinkerers to go and start playing with that architecture, start building software against it, start contributing to kernel development, and basically just prepare it to be consumer ready in the future. And I guess one thing to keep in mind here is that x86 and ARM, they're both decades old at this point. They're 30 to 40 years old as architectures.
That's older than me.
It's older than me too.
Nice.
But RISC-V as an organization started in 2010. The first commercial chips were available in 2016 or 17 or so, or even later than that maybe. This JH7110 launched a year ago or so, or a year or two. And really there aren't very many consumer-ready products that are using RISC-V in any form. And so the purpose of this is to just help accelerate that ecosystem by making a consumer-ready form factor for it. And so as we look at the board, obviously we've had to make some trade-offs there. That chip, it is not competitive from a performance perspective with something like a modern Intel or AMD CPU like we have in our other framework laptop mainboards. It's really more of a Raspberry Pi level of performance with those quad Sci-5 U74 cores. And in addition to that, because of that processor selection, we're limited to soldered memory. So we've got 8 gigs of LPDDR4X on here, which again is enough to get Linux going, do software development. It maybe is not enough for real consumer-ready workloads. And then some other constraints just based on the capabilities of the processor. It really only has a single display output. And so we do, of course, send that display out over the display header that's on the mainboard, so you can use it with the internal display. And then it's also muxed to one of the USB-C ports. So unlike our normal framework laptop that has 3 to 4 display outputs over USB-C, we've got one. And then the other USB-C ports are just USB 3.1 or 3.2. So definitely a bit more limited. And then a few other limitations, like obviously we don't have an NVMe slot because the one PCIe interface that was still available on this is going for Wi-Fi instead. And so for storage, we've got a micro SD socket on the board. And then we've got a little socket for eMMC that's a bit faster. It's not technically a standard socket, but we've seen it used on a lot of single board computers, so it's easy to find modules that'll drop in. But otherwise, like most of the interfaces would work. So things like audio over the FPC that we have here, the speaker connector, the webcam, Wi-Fi. So like basically enough to start playing with and bringing up a full system.
So what are some projects that developers and hardware tinkers could create with this mainboard?
Yeah, sure. So, the two interesting things are, one, actually dropping it into a framework laptop and basically trying to use it. So it's this idea that if you want to help advance the RISC-V ecosystem, probably one of the best things you could do is actually attempt to use it as a main computer for like an extended period of time. And as you dig through the stack of like, okay, why is this thing not working or slower or jankier than it should be, figuring out like, oh, it's because of this, this software is missing this capability or missing some specific interface to an accelerator that's on there or something, and just helping to drive the advancement of that. Obviously, that's not something everyone can do. That's something that if you're a software developer, you can, especially a system level software developer, you can dig into that. Also, we expect that people pick up the Cooler Master case, drop it in there, and similarly, actually just try to attempt to use it as a desktop system for development. So it really, really more focused as a developer system than a consumer system.
What is the, knowledge level that you should know before purchasing one of these to make sure that you have a positive experience playing with the RISC-V system?
Yeah, this is a tricky one. Probably if you're not capable of, or if you're not familiar with, I'll say everyone's capable with enough time and like energy output put into it. If you're not familiar with potentially being able to, let's say, like download a patch for a kernel, recompile a kernel, and like load it and run the system, probably it's going to be a bit early to jump into this specific mainboard today. But we also do expect that as like tinkers and developers and like early adopters start picking up this specific board, playing with it, and maturing the software around it, that it will then become more mature for like the next level of, let's say, like tinkers who are not necessarily going to be compiling code, but want to play with it anyway.
What are you hoping that we as a company are able to contribute to the RISC-V open source ecosystem? Yeah,
so we really actually, for one, hope that this is not the only third-party mainboard, not the only RISC-V mainboard that ever shows up. Obviously, the team at DeepComputing is doing awesome work with this. They've got some interesting ideas for potential future stuff on the roadmap. But the intent here really was that this was the first RISC-V mainboard in a kind of consumer-ready laptop, and also the first third-party mainboard for us as a company. And it's actually been kind of like a pipe cleaner for everyone. So in working with DeepComputing on their mainboard, we've actually developed a bunch of documentation that they needed to actually make this work. So, we have on GitHub today is kind of like a subset of what we've been working on with them. Obviously, as we develop and prove that it functions, we'll release all that on GitHub as well. But it means that now any third-party hardware developer, whether it's DeepComputing or someone else, is going to have a much easier time creating a compatible mainboard. And also, similarly, as part of this, because of all the work that DeepComputing is doing to kind of almost consumerize RISC-V, they're doing a bunch of work with RISC-V International. They're doing a bunch of work with the team at Canonical who make Ubuntu. They've been working with a number of other Linux distributions, maintainers and developers there. Basically, it is just this very interesting collaborative pipe cleaning exercise to pave the way for future RISC-V consumer products.
It's like, how can we as a consumer electronics industry work together to make the future of consumer electronics more accessible and open for everyone?
Yeah, absolutely.
Not just big business.
Yeah, and going back to like RISC-V really as like, high performance ready architecture is only a few years old. If we look out 5 years or 10 years, there's like a really, really exciting potential for this to be this rich open ecosystem with a number of core developers, a number of chip developers, a number of mainboard developers, a big, rich software ecosystem. It's all really, really exciting.
Why is open source so important for consumer electronics?
Yeah, sure. This is an interesting one. It really comes down to this idea that with an ecosystem with like multiple competitors, with multiple entrants, with multiple collaborators, that you can get better results than you can by a single company trying to own and manage and maintain a thing and basically having the business priorities that that company believes are the right ones. By having actually at this point dozens of different chip makers all licensing RISC-V cores and dozens of different core developers all creating their own cores, there is this really interesting competition that's occurring out there, and people are open sourcing things, people are sharing ideas, people are, pooling their different architectures together in a way that just enables this rapid advancement. And we can see that in the software space, of course, with things like Linux as a whole, where because there are thousands of developers contributing to Linux and thousands of different end use cases or millions of different potential end use cases, the richness of Linux enables like these super interesting applications all the way from like the tiniest little embedded systems all the way through, massive data centers that are Linux focused or user devices or, the billions of Android phones that are out there. And RISC-V is similar. Like RISC-V, actually, secretly, we've had a RISC-V core in the Framework laptop since day one.
Oh, really?
Which we didn't realize until recently, but actually our fingerprint reader has a RISC-V core that's just doing like little housekeeping tasks in it. And now all the way to the main core processor in the system being able to be RISC-V. You can imagine a future where every processor core, which there are actually dozens of across something as complex as a laptop, could follow this common instruction set architecture and be able to plug into the same software ecosystem.
And so that also makes it simpler for the engineering teams to be able to debug and do all
In many ways
work.
it does, yeah, and that enables common tooling across different applications, common
That's
debug
nice.
cores. Yeah, common compilers.
Do you have a RISC-V project that you'll be tinkering on with your mainboard?
Well, as soon as we ship this, or rather as soon as Deep Computing ships this, and of course we will be reselling the Deep Computing board that they're developing in our marketplace, I am going to try dog fooding it as an end user, basically putting it in my own personal Framework laptop, using it for a week or two and just seeing like, okay, how ready are we? And then what do we need to invest in as Framework? What does Deep Computing need to invest in? What do the Linux distros need to invest in to actually make it consumer ready in the future?
Have you been dog fooding this mainboard?
I've tried it. I've used it. Actually, we do have a few folks on the team, our firmware team, Kieran, Alex, Daniel, and actually our intern B have been playing with it and basically been just testing out what's working.
So the RISC-V mainboard will be available on the Framework marketplace
as soon as it's ready. So ultimately, of course, this is Deep Computing's product. So this is their EVT build, actually. So their first functioning boards that they've been bringing up. They are currently in development on their DVT boards. And obviously, they've been doing a bunch of validation work. As we've been testing, we've been providing them some feedback as well. But largely from like a capabilities standpoint, a feature set standpoint, this is representative. But obviously, there's a cycle of maturity through the development process that they need to go through. They need to go through the certification process to actually be able to sell this as a product. But then, of course, once it's ready, we will be selling it through the Framework marketplace.
How do we anticipate the pricing will be compared to our current mainboards available?
Yeah, this is an interesting one. Because it's really more aimed towards developers, the pricing and just the capabilities of that CPU and what's on this board, you can see it's there's a less going on there than there is on an Intel or AMD mainboard that we have. And so the pricing is going to be more like a high-end Raspberry Pi with a few add-on boards, more than something like an Intel or AMD mainboard. So it's really, pricing-wise, the Deep Computing team is really trying to make this accessible for developers to play with.
Well, maybe that's what we can use as like our copy byline. It's like a luxury Raspberry
That's
Pi.
right. Yeah, I like that.
Thank you so much for watching. If you have any questions about RISC-V, deep computing, or other things in the hardware open source space, just leave them down in the comment section below, and we'll catch you guys next time.
Awesome. Thanks.